Now we will talk about symmetry operations. And symmetry operations are important because that's how we classify the crystal lattices. So we look at the set of rigid operations that take the lattice into itself, and we call this set the symmetry group or space group of the lattice. Now, if you look at what can be in this group, the full symmetry group of a Bravais lattice consists of operations of three different forms. It could be translations through lattice vectors. So these lattice vectors are vectors of the form R, which is n1a1 plus n2a2 plus n3a3. When we do these translations, if we have a symmetric situation, it's called translational symmetry. The second type is operations that leave at least one lattice point fixed. So these are called point operations. These could be rotations, reflections, and inversions. And the third possibility is operations that have a combination of 1 and 2 that gives us a symmetric situation. Okay, so we will take a look at these point operations in more detail. So the first one is rotational symmetry. So this is basically defined by the fact that there exists an axis such that if the lattice is rotated around the axis through some angle alpha, the lattice remains invariant. So here is the example. This is a square lattice. So if we rotate this lattice by 90 degrees around point B, we will see that the lattice remains invariant. Also around point C, we will see that the lattice remains invariant. And if we rotate by 180 degrees around an axis that goes through point A, we will see that the lattice remains invariant. So which ones of these operations are point operations? Well, we need to consider which operation keeps a lattice point fixed, and that is the operation about an axis that goes through point B, so that is the point operation, whereas the rotation operations around point C and point A are not point operations. So when we have this perpendicular axis that goes, or perpendicular plane that goes through point A, which is not a lattice point, the lattice remains invariant under a rotation of 180 degrees. So we note that that is 2 pi divided by 2. So that's not a point operation. An axis through point B allows 90-degree rotations. So if we have a rotation about this axis by 90 degrees, the lattice remains invariant, which is a point operation. So that is 2 pi over 4 rotation. And an axis through point C allows 90-degree rotations, but it's not a point operation because it doesn't keep a lattice point fixed. Okay. Now, if a lattice remains invariant under a rotation of 2 pi over n, where n is an integer, we say that the lattice has n-fold rotational symmetry. So here is a square lattice. I have labeled points 1, 2, 3, 4. The lattice constant is A. So if I rotate this by 90 degrees about point 1, after a translation by minus A, so first I translate these points with a vector minus A j hat, if you wish, we call this y-axis. Then this would be basically minus a j hat would be the translation. And then I rotate the lattice by 90 degrees about an axis that goes through point 1, that is perpendicular to the plane of the lattice. And what do I see? For example, if you concentrate on point 3, if I rotate this by 90 degrees with respect to point 1, an axis that goes through point 1, you can see this 90 degrees rotation would map 3 to upper right corner. And similarly, you can see that 2 would be in the upper left corner, 1 is fixed, and 4 would be in the bottom right corner. So this rotation by 90 degrees around point 1 is a point operation, and it's basically mapping the lattice into itself. So it's basically describing a 2 pi over 4 rotation is basically not changing the lattice, and therefore we have a fourfold rotational symmetry about an axis that goes through point 1. And the translational symmetry requirement limits n to be 1, 2, 3, 4, or 6. So there is no five-fold rotational symmetry. So let's prove this. Now I'm taking two lattice points A and B. Those are the nearest lattice points to point X, where X is on an axis of rotational symmetry at a distance r from A and B. So X doesn't have to be a lattice point. So this is X in the middle. A and B are at a distance A from each other. They are the nearest lattice points. So if I have a counterclockwise rotation by an angle alpha, you can see that this would take A to B. So A would be taken to point B when I rotate by an angle alpha. If I rotate by an angle alpha in the clockwise direction, however, it would take A to point A prime. And the counterclockwise rotation would take point B to point B prime also. So if this lattice has rotational symmetry for this angle of rotation alpha, A prime and B prime would be two lattice points that are at a distance A prime from each other, but they should be lattice points. So therefore, since I have a parallel situation here, this A prime has to be an integer multiple of A, which is the nearest neighbor distance in this lattice. So A prime must be S times A. So counterclockwise rotation by an angle alpha takes A to B, B to B prime. Clockwise rotation by an angle alpha takes A to A prime. And A prime and B prime must be lattice points because I have symmetry for this rotation. And A prime is an integer multiple of A because it's the same angle alpha that I'm doing this rotation clockwise or counterclockwise. And therefore A prime and B prime should be on the same line, and therefore A prime must be lowercase a prime, the distance between A prime and B prime must be an integer multiple of the lattice constant A. So how can I find the relationship between angle and A? So if you look at this triangle here, this is the base, and I drop a perpendicular and it's 90 degrees. So the distance from the point X to points A and B I called X. So this distance is X. So this angle is alpha over 2 and this angle is alpha over 2. So that distance I called R, not X. So this distance is R, this distance is R, and alpha over 2, alpha over 2. So R sine alpha over 2 will give me half of A. So 2R sine alpha over 2 is A. And A prime would be similarly, if you look at this is the base now, and here is the perpendicular. I drop here, and this is gamma over 2 and this is gamma over 2, and I would find that A prime is 2R sine gamma over 2. So since 3 alpha plus gamma is 360 degrees, gamma is 360 minus 3 alpha, and A prime is 2R sine gamma over 2, which is sine 180 minus 3 alpha over 2, and sine of pi minus x is sine pi cosine x minus cosine pi sine x, which is sine x. Because the first one is 0, the second one gives me cosine pi minus 1 minus minus becomes sine. So it's sine x. So this is 2r sine 3 alpha over 2. Now, as I said, this a prime, the distance between the two lattice points a prime and b prime, must be an integer multiple of a, that is 2r sine 3 alpha over 2. This is my a prime distance, must be an integer multiple times 2r sine alpha over 2. So this is basically a, and this is a prime, so it's s times a. So that gives me the following requirement: sine 3 alpha over 2 to sine alpha over 2 ratio must be an integer. So if I remember my trigonometric identities, sine 3x is sine x plus 2x, that is sine x cosine 2x plus cosine x sine 2x. For sine 2x I can substitute 2 sine x cosine x. For cosine 2x I can substitute 1 minus 2 sine square x, and sine square x plus cosine square x is equal to 1. So sine x cosine 2x becomes sine x 1 minus 2 sine square x, and plus cosine x 2 sine x cosine x becomes 2 sine x cosine square x. So if I distribute sine x to the parentheses, sine x minus 2 sine cube x plus 2 sine x cosine square x, I can substitute 1 minus sine square. Sine x minus 2 sine cube x plus 2 sine x distributed into the parentheses, I have 2 sine x minus 2 sine cube x, which gives me 3 sine x minus 4 sine cube x. So sine 3 alpha over 2 with that becomes 3 sine alpha over 2 minus 4 sine cube alpha over 2. So this ratio S is sine 3 alpha over 2 to sine alpha over 2 becomes 3 sine alpha over 2 minus 4 sine cube alpha over 2 divided by sine alpha over 2. Sine alpha over 2's cancel, I get a 3, and I get a minus 4 instead of sine cube, it becomes sine square alpha over 2. So you can see that sine square alpha over 2 is 3 minus s over 4. Well, we know that sine is a function between minus 1 and plus 1. However, sine square is a function between 0 and 1. So 3 minus s over 4 must be an integer between 0 and 1 because s is an integer. So we have, no, well, s is an integer, so 3 minus s over 4 is between 0 and 1. It doesn't have to be an integer. Okay, so if I multiply both sides with 4, I obtain 0 less or equal to 3 minus s less or equal to 4. If I add s to all sides, I get s less or equal to 3 less or equal to 4 plus s. So s should be less or equal to 3, and on the other hand, I have 3 minus 4 is less or equal to s, or s is greater or equal to minus 1. So s is an integer between minus 1 and 3, including the boundaries. So if I substitute s equals minus 1, then sine square alpha over 2, which was 3 minus s over 4, becomes 1. And sine square alpha over 2 equals 1 implies alpha over 2 is plus or minus pi over 2, which is basically implying alpha is plus or minus pi, or 2 pi divided by an integer, so that integer is 2. When s is equal to 0, I obtain sine square alpha over 2 is 3 minus 0 over 4, which is 3 over 4. So sine alpha over 2 is plus or minus square root 3 over 2. And alpha over 2 is plus or minus pi over 3, so it's 60 degrees. Sine 60 is square root 3 over 2. And alpha is plus or minus 2 pi over 3, or 2 pi, it's in the form 2 pi over n, where n is equal to 3. When s is equal to 1, I have sine square alpha over 2 is equal to 3 minus 1 over 4, which is 1 over 2. That is sine alpha over 2 is plus or minus 1 over square root 2, or square root 2 over 2. that corresponds to 45 degrees, so plus or minus 45 degrees, alpha over 2. So alpha is plus or minus 2 pi over 4, so n equals 4. If I substitute, however, s equals 2, sine square alpha over 2 is 3 minus 2 over 4, which is 1 over 4. Sine alpha over 2 is plus or minus 1 over 2, that is 30 degrees. So alpha over 2 is 30 degrees. Alpha is plus or minus 2 pi over 6. N equals 6. You see 2, 3, 4, and 6. We don't have 5. And for s equals 3, on the other hand, if we go through the math, we find n equals 1. So we find that only 1, 2, 3, 4, and 6-fold rotational symmetries can occur in a Bravais lattice. N equals 5 is not allowed. So this is basically what we see for the rotational symmetry. Now, as for the mirror symmetry or reflections, we consider the lattice points on either side of a line or a plane in 3 dimensions that are mirror images of one another. So here is our square lattice. So you see this imaginary line that goes in the middle between points A and B. You can see that the left hand side is the mirror image of the right hand side. So this is an axis of mirror symmetry or mirror symmetry axis. The same thing is true for 3-dimensional lattices, but now we would say it's a mirror symmetry plane. Okay, and the third possible symmetry is the inversion symmetry. So a cell has an inversion center if there is a point at which the cell remains invariant under R to minus R transformation. And all Bravais lattices are inversion symmetric. So here is our square lattice. Point X is an inversion center. I look at the vector R that takes my inversion center to point A, and if I have an R to minus R transformation so that A is translated to where point B used to be and B is translated to where point A used to be, I see a completely symmetric situation. So X becomes an inversion center. And this one is a point operation because it was a lattice point that I have chosen for the inversion operation. Okay, so let's summarize the symmetry operations. Well, first of all, why are these operations important? Because they let us classify the lattices. So crystal lattices are identified by their symmetry group. What is symmetry group? It's the set of rigid operations that takes the lattice into itself. And the full symmetry group of a Bravais lattice consists of 3 possible types of operations: translations, point operations, rotations, reflections, inversions, and number 3, a combination of 1 and 2. And the point operations as for the rotational symmetry, if we choose a lattice point and we look at the rotational symmetry of the lattice about this for an axis that goes through this lattice point, we see that this is a point operation, and here I have shown this symmetry with a square for point B. You can see that I have a 2 pi over 4 rotation that maps the lattice into itself. So that's basically what we call a 4-fold rotational symmetry for the square lattice. And as for point A, we have a 2 pi over 2, 180 degrees rotation that maps the lattice into itself, but that's not a point operation because A is not a lattice point. And similarly for point C, which is not a lattice point, we have a 4-fold rotational symmetry. So if a lattice in general remains invariant under a rotation of 2 pi over n, where n is an integer, we say that the lattice has n-fold rotational symmetry. So in this example, I have taken the square lattice and translated it by minus aj hat, so that I map the lattice into itself, but 1, 2, and 4, and 3 are now at the bottom side. And then I have performed a rotation of 90 degrees about an axis that goes through point 1, perpendicular to the plane, and basically that is going to map, here I demonstrate 3 from the bottom right corner to the top right corner, and 2 will be translated to the top left corner, etc. So this is basically again a point operation that is a combination of translation and rotation. Okay. The translational symmetry requirement limits n to be 1, 2, 3, 4, or 6, and we have proven that a 5-fold rotational symmetry is not possible for a Bravais lattice in this example. And finally, for the reflections, we have a mirror symmetry axis in 2D or a mirror symmetry plane in 3D. When we look at all points that are on one side of the mirror, the other side has a completely reflected version, and basically it's all points are invariant under mirror reflection for this mirror symmetry axis or mirror symmetry plane. As for the inversion symmetry, a cell has an inversion center if there is a point at which the cell remains invariant under R to minus R transformation. So if I map all points at position vector R with respect to the inversion center to minus R and vice versa, so then I find that the lattice maps onto itself, and X is an inversion center, so the lattice has inversion symmetry. And all Bravais lattices are inversion